All right, so today we're going to be talking about, or in this video we're going to be talking about partitions, revisited and refined. So to motivate what we're going to talk about today, let's think of, or let's consider two functions. Let's say we have a function, some f of x, and we want the area between a and b. And then we have some g of x, let's say like that. And let's also say it's between the same a and b values. Now, let's say I have a partition for f. So I have a partition that I'm using here, which I will call p. So p is some list of values, some x0, x1, up to xn, where importantly this is a and this is b, right? And I have some other partition q, which is some y0, y1, ym. So to draw attention, they may not even have the same number of points. But again, I have y0 is a, ym is b. And let's say I build these partitions to do something. Maybe I'm calculating some upper and lower sum. So I want to do something with like, oh, I have the upper sum with respect to p on f, right? And I know that's a thing, equals something. And I have some upper sum with regards to g, sorry, wrong order, with regards to q and g. And this is some other thing. So one thing we might want to ask about is, do we know anything about, say, the upper sum of, I'm going to deliberately sort of not put something here, f, let's say f plus g. So this kind of thing comes up a lot. And in fact, we're going to run into this sort of very systematically and cover it very carefully when we talk about properties of integrals, Riemann integrals, and we talk about what do you do when you're going to do the sum of functions or try to split an integral over an addition sign, which are things we know we should be able to do from calculus. But just as we sort of have seen, this course is more about taking all the things you sort of did freely in calculus, and now we don't get to do them so freely. We have to actually rigorously go through them. So the problem is that if I want to talk about u of a function, even if that function is the sum of some other functions I know stuff about, I need a partition that I use. But I can't use p here, because even though I know about stuff about f, how it's linked to p, g never had p, right? It used q. Likewise, I can't use q because f has nothing to do with q. So I shouldn't say I can't use it. I could, but I don't know anything about how that other function reacts there. So this sort of motivates the idea of taking some sort of set that gives us enough information about both functions. And sort of off the top of your head, you might come up with a number of ways to do this. But it turns out there's sort of one obvious right way of doing this. And to understand why it's the right way, I'm going to step back a little bit and remind ourselves, this is something we did when we talked about the actual notation bit in that video. If I were to cut this up, so if I were to say, OK, let's cut it up here and there, let's say, then my upper sum, let's say in this middle piece, my upper sum would have this rectangle, right? But if I added another slice, instead, let's say I did this piece, I added some point in between, then my upper sum would have, instead, this middle piece would drop down there, and I'd have a new rectangle formed here. So in particular, maybe I should have drawn that bigger, but in particular, this box in the top right here would go away. So my new upper sum would actually be smaller if I injected another point. OK, okay? This is a theme that's going to come up throughout the video. So if I add more points, because my upper sum is getting smaller, I'm getting, or even just looking at it, you can tell, you're getting a more accurate representation. You're getting a more accurate approximation by adding more points. Now, I want to be very clear that there's a distinction between having more points and adding more points. Because it is possible that instead of having, right, 1, 2, 3, 4 versus 1, 2, 3, 4, 5, I could have 5 points that have a worse approximation if I moved all the points to the right spots. So it's not just that I have 5 points, therefore it's better. It's that I added a point to the existing 4. Okay? I didn't move the original 4 points, I added one to it. That's key. So adding points will definitely make it no worse of an approximation, but that is not the same as saying having more points will be no worse of an approximation. That is definitely possible, okay? And if you guys want, I can maybe do a video sort of going more in depth there. Regardless, when we add points to an existing set, this is what we call a refinement. So, a refinement of a partition so if I called a refinement, let's say R, of a partition, I don't want to use those, so let's say a partition S is a superset, i.e., if I have a refinement R of some original partition S, that means that S is a subset of R. Okay? Some people might go so far as to say that it is a strict subset. I'm not going to worry about that distinction at the moment. The point is that R definitely has all the points of S, and probably more. And that's what we mean by refinement. Okay? And the more refined a set is, meaning the more we keep adding points to it, the better of an approximation we get, okay? So coming back to our idea here then, we want a set where we have information on G, information on F, so that I can use F and G, but I have these sort of possibly distinct, maybe have nothing to do with each other partitions. So the sort of standard technique to use is to create R, or some set, I'm calling it R, it's not always R. So to create some refinement set, I'll call it R, that is simply P union Q. So you sometimes will see this as listed as the smallest set that contains both P and Q, which is at this level by definition P union Q. So I'm going to take a set that is simply the union of both of those and use that as my new set. Now this isn't to say that this doesn't create problems of its own, because it will, and we'll talk about that when we get to that later. But this is sort of, as it turns out, the right way of going about it, because it gives you enough control, enough information about what's going to happen with F and what's going to happen with G to tackle things like F plus G, okay? So this set R is sort of the standard way of going about forming some sort of joint base from which to tackle things that use more than one partition originally. This is a little vague because we don't have the sort of tools to do the examples yet. I just want to sort of explain not just what it means to have a refinement, which is what happens in the section of the book that we're talking about right now, but sort of why we care in the first place. So this is definitely going to come up a lot. This is a very standard technique to refine one set with another set in order to get some sort of joint set you can work from, okay? So last but not least, I want to sort of formalize the statement I was making earlier, this statement here, which is that a refinement R of some set S, right? The set that has everything in the original set plus more will always have a quote unquote better approximation. So what does that mean? Well, this means that if you have some, let's say, lower approximation of f with this s, what's it mean to have a better approximation than s when I'm using r of f? Well, remember, the lower sum is the sum that is too small. But in some sense, I want it to be as close to the real sum as possible. So if I have a better approximation, it should still be too small, but it should be less so, meaning that the better one should be a bigger approximation because it should be less small of an underestimate. This is, right? Does that make sense? So the better version, the refinement, will be a bigger actual number, right? Because these are numbers, remember, once you get them all calculated, even though it is itself still a lower approximation. Sort of similarly, if I used an upper approximation, S and F, versus the refinement, again, what does it mean to have a better approximation? If I add in another value, I'm going to have still an estimate that is too big, but it'll be less big than the worse approximation. So the refinement will have always a approximation that is no bigger than the less refined version. And this, again, this is one of those things that we're going to use a lot, because that's how we're going to sort of get around a lot of the problems that we're going to have doing this stuff, where we're like, I don't actually know how f depends on r, but because r is a refinement of p, and I know how f works on p, I can say something about how f works on r in this way, okay? So this idea is what you want to take away from the refinement, and we're going to use this at length when we talk about this stuff, probably in, I think, 6.2 and 6.3. All right? So that is our refined understanding of partitions. Ba-dum-bum. All right, that's it.